How do you actually stop a powerful AI from doing something dangerous? For years, the answer has been, well, a mix of guidelines and a whole lot of hope. But what if we could move from just hoping an AI is safe to proving it with mathematics? That is the incredible promise of a new framework called CAST. It's designed to give us a mathematical guarantee of safety for AIs that can actually act in the real world. Let's dive in.
So here's our game plan for this explainer. First, we're going to explore the brand new kind of Wild West world of tool-using AIs and the risks they create. Then, we'll see how CAST turns all that chaos into a clean, simple problem of geometry. After that, we'll meet the unblinking monitor that acts as a digital guard. We'll apply it all to a high-stakes financial scenario, and finally, we'll really grasp why this is such a monumental shift from hope to actual proof in AI safety. All right, first up, the tool-using AI problem. The best way to think about this is like giving a brilliant but totally unpredictable apprentice a set of very, very powerful tools.
You see, the huge shift happening right now is that AIs are breaking out of the chat window. They're not just talking anymore. They're becoming agents, actors that can pick up digital tools and directly mess with the world around them.
And we're not talking about simple calculators here. A perfect example is giving an AI the ability to write and execute its own computer code, say, in a Python interpreter.
This ability to use tools is a massive power-up. It lets an AI analyze data, talk to other systems, and change the digital world in ways that were just impossible for a model that could only generate text. It's like giving that apprentice the keys to the entire workshop.
But with that power, well, you know what they say. It comes with enormous risk. How do you make sure an AI with the power to run code doesn't manipulate a financial market or accidentally wipe a critical database? The safety methods we have now are kind of like Band-Aids. They're just not built for this level of raw power. And that leads us to the billion-dollar question, maybe the trillion-dollar question. How do we build a safety system that we don't just hope works, but one that we can mathematically prove will work every single time? This is one of the biggest challenges in all of AI today, and frameworks like CAST are right on the cutting edge. If you want to stay ahead of the curve on the solutions being built, now is the perfect time to subscribe.
This is where CAST comes in, and it proposes a completely new way of thinking about the problem. Instead of trying to predict every possible bad thing that could happen, CAST just reframes the whole thing as a problem of geometry.
The core idea is brilliantly simple. It's called the safe set. Think of it like this. Imagine a giant map of every possible action an AI could ever take. The safe set is like drawing a very specific safe zone on that map. Now the key is that this zone has to be a convex shape, which basically just means it has no dents or holes in it. This simple rule makes all the math work. If the AI's proposed action lands inside this zone, it's safe. If it's outside, it's a no-go. Simple as that.
And this slide shows it perfectly. That green box, that's our safe set. When the AI wants to do something, that action is like a point on this map. If it's the green dot inside the box, it's approved, all good. But if it proposes something unsafe, like that red cross way outside the lines, it gets flagged. Now here's the really clever bit. Instead of just saying no, the system can use math to find the closest safe action. That's the blue arrow, literally dragging the bad idea to the edge of the safe zone. It's not just blocking danger, it's course correcting it with math. This idea is a total game changer, and we're about to see how it works in the real world of finance. So stick around for that. And hey, if you're finding this deep dive valuable, now's a great time to hit that subscribe button. So we have this geometric safe zone. But who actually polices it? Who's standing guard? Well, that is the job of what the paper calls the unblinking monitor, the system that watches over the AI in real time.
Here's how this gatekeeper works at every single decision point. First, the AI comes up with an action it wants to take. Before anything happens, the CAST monitor hits pause on the whole system and runs its checks. It uses its own secret randomness to test the action against the safe zone's boundaries. If the action is safely inside that geometric zone, a certificate gets issued and the action is released. If it's not, a safe fallback is triggered instead. It is a gatekeeper that absolutely nothing gets past.
This chart really gives you a peek inside the monitor's brain. Think of it like a really, really good smoke detector. That green line at the bottom is a safe action. It's like clean air, so the alarm stays silent. But the red and orange lines are unsafe actions. That's the smoke. The monitor's internal math is built to detect even a tiny whiff of it. And once it does, the alarm signal doesn't just rise, it grows exponentially. It screams danger almost instantly,
hitting that rejection threshold and stopping the action before it can do any harm.
Okay, this all sounds fantastic in theory, but does it actually work in practice? Let's ground this whole thing in a high-stakes example straight from the research paper, financial trading. So here's the setup. We've got an LLM that uses a Python tool to analyze data and predict what's going to happen with stocks the next day. The safe set here is defined by crystal clear rules. The AI is absolutely forbidden from making predictions that could look like market manipulation or that take on way too much financial risk. The cast monitor is the ultimate gatekeeper, checking every single prediction before it can be acted on.
And here is how it plays out step by step. The LLM proposes a trade. The cast monitor instantly checks if this proposed trade respects the geometric boundaries of our safety laws. If it's inside the safe set, great, it gets certified. But if it's outside, say it looks like it's trying to start a pump and dump scheme, it gets rejected instantly. The system then just defaults to a pre-approved safe action, like no trade, or it mathematically finds the closest possible safe trade.
So what does this all add up to? Well, it's a fundamental shift in how we approach AI safety. We are moving from an era of just hoping for the best to an era of mathematical proof.
I just have to read this quote directly from the paper's conclusion because it is so powerful. It says that for any safety rule you can define with this convex geometry, you can build a practical, efficient gatekeeper that provably enforces that rule. The takeaway here is huge. This is not just a theory. This is a blueprint for building AI systems we can actually genuinely trust.
So why does this matter so much? Well, it takes safety from being a vague art to a precise science. It provides what the paper calls finance-grade containment, which is exactly what you need for high-stakes stuff. It transforms the terrifying idea of unlimited risk into a measurable, auditable risk budget. And it creates a formal, mathematical contract for what safe actually means. A contract that holds up even in the complex, messy world of tool-using AIs.
Now, this is not a silver bullet. The paper is very honest about the trade-offs, which are captured in something called the verification trilemma. Basically, you can pick 2 out of 3, having incredibly detailed safety rules, having rules that cover every single possibility, or having rules you can check really, really fast. You can't have all 3. CAST makes a smart choice. It prioritizes rules that can be efficiently verified, giving you rock-solid guarantees for those specific, well-defined boundaries.
Which leaves us with a final and I think really important question. As these AI systems move from being simple tools to powerful agents that can act on our behalf in the digital world, is a system like CAST, one based on mathematical proof rather than just hope, the only acceptable standard for safety going forward? Let us know what you think in the comments, and be sure to subscribe for our next explainer.